Hello, everyone. It's me, Billy Younger, again for PhysicsSolutions.com. I just wanted to take a minute to solve a problem that I know some of my Physics 202 students are having problems with. I'm not quite there yet in my 241 class, so this is not necessarily useful for them yet, but it definitely will be. So this will be good for what we call 202 and 241, which is the algebra-based physics in the 202 case, and the 241 is calculus-based physics. So this will be good for algebra-based or calculus-based physics because I'm not using any calculus, but I am working on the outer limits of the tougher stuff that you have to do normally for a 202 course. So in this video, which I call Coulomb's Law Part 1, Force, and specifically what I'm talking about is I'm going to define Coulomb's Law or give you Coulomb's Law, specifically the version of Coulomb's Law in which you're using a formula to find the force. There's another version of Coulomb's Law that you can use to find the electric field. We're not there yet, so I'm just doing the Coulomb's Law for force, and that's what I'm calling Part 1. So we're going to start off by me giving you a description of Coulomb's law with all the relevant facts because it's more than just a formula. It actually has some sentences that accompany it and stuff of that sort. So let me start by going ahead and sharing my screen with you all. So I'm going to share screen from my iPad. This should pop up momentarily. So it should come up in any minute now. Now, when you look at it, you're going to see that I have Coulomb's law and then parentheses force, close parentheses, part 1. Of course, I wrote all this in cursive because cursive is a lot more efficient way of writing. If you're writing sentences in many words, you need to write in cursive because it's so much more less time consuming and saves so much more time. I then decided, because I'm doing this for everyone, I know there's a lot of people that just have never been taught cursive, so I did decide to go ahead and type it. But be assured this says the same thing, essentially the same thing as the other version. What is a little bit preferred here is notice that I was able to write Q1 and Q2 with actual subscripts. So you can see Q1 and Q2 with subscripts. I can also write powers of 9, or excuse me, powers of 10, which in that case was 9 and 10 to the negative 12th, and a subscript down here. And I can put Greek in because this is the Greek letter epsilon. I hardly ever use the K, but it is a much more quick use to use K when you're just calculating the force. So I am using it this time, though I usually don't use it. So that's the only thing I'd really want to point out that's a little bit better in the handwritten version, is that I could actually write subscripts and Greek letters and superscripts and that sort of stuff. Here's the actual version in typeset, and it says Coulomb's law, parenthesis force, part 1. As I said, part 2 will come later when we're actually do it with the electric field as opposed to the Coulomb law of force. It says the force of attraction or repulsion between 2-point charges, Q1 and Q2, is directly proportional to the product of the magnitude of the charges, inversely proportional to the square of the distance between the point charges, and that's called R, and acts along a straight line that passes through the 2-point charges. Note, if the charges have opposite signs, for instance, one's positive and the other one's negative, then the force is attractive. If they have the same sign, i.e. they're both positive or they're both negative, then the force is repulsive. Then there's another note. Any spherical distribution of charge behaves exactly like a point charge at the center of that sphere, as long as you're only considering the force outside the body of the charge distribution. And then, of course, I gave you what the actual constants are, but I had to use caret symbols to show exponents, and I just wrote out the Greek word epsilon dash 0 for epsilon 0. I also call that epsilon naught, which is another way of saying epsilon 0. So just be in mind, keep that in mind in case you hear anybody else say epsilon naught or something like that. Now that we have the force, notice it not only gives us some facts about it, we know that it's directly proportional to the product of the charges. So if you found one charge distribution that gives you a force of 100 newtons, if you replace one of the charges with a charge twice as big, that force would now be 200 newtons. If you replace instead one charge with a charge twice as big and the other charge with a charge 3 times as big, then that would be 2 times 3, 6. So it'd be 6 times 100 newtons in that case. Additionally, if I had two charges that had a force of 100 newtons attracting or repelling them, If I separated them by twice as big a distance, then I'd have to take that 100 newtons and divide it by 2 squared, which is 4, and that would give me 25 newtons. If I actually cut the distance in half, let's say if I cut the distance to a third, okay, so I went from like 3 meters to 1 meter, then the distance got smaller, and since it's inversely related, that means the force got larger by a factor of 3 squared, which is 9. So in that case, going from 3 meters to 1 meter would make the force go from 100 newtons to 900 newtons. So it has a lot of concepts in there. Plus, it tells you exactly the direction, which is what we need. For vectors, we need magnitude and direction. So now that I've got that cleared, let's go ahead and attack a specific problem. Here's the problem I made up. It says, what is the total force on Q? That means the capital Q. Notice I have a capital Q in the bottom left. I have a lowercase q1 in the bottom right, and then a lowercase q2 in the top. And what I'd like to calculate is the total force on capital Q. So what I'm going to do is I'm going to mark off the area where I'm going to write the solution, and I'm going to do that with neat lines. So I'm using this little drawing tool that allows me to make crappy lines, and then it'll turn them into straight lines. So I'm going to do that. I'm going to go over here and do that. Then I'm going to go over here and then down to here, and then here. Okay, so now I can see where the solution is, and I'm going to go ahead and write up here solution. Whoa, Nelly. I got to take it off that automatic draw program because it doesn't like letters and stuff like that. So solution. So the first thing we got to realize in doing such a problem is force is a vector quantity, and therefore it obeys vector laws. And what we learned in the first semester of this course was that forces add like vectors. So basically the force on capital Q total is the force on capital Q due to Q1 plus the force on capital Q due to Q2. If I had 15 of them, I'd have 15 of those terms I have to do. But in this case, 2 is sufficient. And I'm going to write that by F total, which I'm also going to call FQ. And I'm going to point out, oops, that Q did not get an underline where I liked it. So let me make that a little better. Okay. And since it's a force and a vector quantity, I put the vector symbol over top of it. And what I'm going to say is, due to the superposition principle or various other ways you might want to think about it, that's equal to the force on Q due to charge 1 plus the force on Q due to charge 2. Notice how I wrote that and how I said that. FQ1 means the force on the charge capital Q caused by the charge lowercase q with a subscript 1. That's what FQ1 means. Similarly, FQ2 means the force on capital Q due to charge lowercase q with a subscript 2. So that's what I have to do, is find those vector quantities and then add them. Of course, finding vector quantities and add them just means that we're basically going to compute the magnitudes, create vectors out of them, and then combine like components of the vectors to get a new x component, for instance, and then combine like components in the y direction to get the new y component, and then work out the whole force. So with that in mind, I'm going to first tackle Q1. So the force on Q due to 1 is going to be 8.988 times 10 to the 9th Newton meters squared per Coulomb squared. So we're just using the formula K, Q1, Q2 over R squared. Q1, notice I'm leaving off the sign, is 9.99 times 10 to the negative 7 coulombs. And then capital Q is, again, leaving off the sign, but it's positive, 1.01 times 10 to the negative 3 coulombs. Okay, that's kind of hard to see in there because I tried to fit it in, but just notice that's supposed to be 1.01 times 10 to the negative 3 coulombs. Let's try writing it again. 1.01 times 10 to the 3, with a negative, of course, coulombs, like that. That's what I multiplied there. Now I've got to divide it by the separation between Q1 and big Q, squared. Now the separation between Q and Q1 is obviously 30 centimeters, so I'm going to write that as 30.0 times 10 to the negative 2 meters, because we have to use the base units when we're using the SI system for equations, unless they tell us otherwise. Now that has to be squared. When we actually do this computation, and of course, whenever your instructor does something like this in class, you should have your calculator out and verifying it too. One, because it helps him or her not make careless mistakes that could cost the whole class having to go back and correct stuff. But two, because it helps you learn what you're doing with the familiarity of plugging in numbers and stuff like that again. So my decimals got a little small, so I want to make sure they were obvious where they were. So I've done that. Now that I've calculated this, this is the Q1, and because it's considerably closer than Q2 is, this turns out to be a much larger force. In fact, this force turns out to be 100.764 newtons. Now you can see I had 4 sig figs, 3 sig figs, 3 sig figs, and 3 sig figs, and it's all multiplication and division. And the rules for sig figs with multiplication and division is that basically, however many sig figs the number with the least sig figs had in it, that's how many sig figs you got to round the answer to. So the one with the least is 3 sig figs, which means the 7, the 6, and the 4 are not sig figs. But in intermediate calculations, which is what this is, I always keep at least one sig fig. I generally keep 2 myself, but in this case, I'm keeping 3 right now. So that's the magnitude of the force on Q due to Q1. Now, remember, the Newton's law, or the Coulomb's law, says that the force acts along a line connecting the point charges. So the point charge, capital Q, is right here, and we assume its center would be right there, and it's a point charge, so that's basically where it is. Similarly, the Q1 is right there, so its point charge is right there at the center. Again, I have to draw along that line, and in so doing, I'm going to go ahead and draw this vector so we'd have some understanding of what it looks like. Now we see capital Q and Q1 have opposite signs. Q1 is negative and capital Q is positive, so they are attractive, and that means the force on capital Q must point towards Q1 along that line. So what I'm going to do is draw a force this way, and that's FQ1, the vector. Notice it only has if I treat the horizontal direction as the X direction and the vertical direction as a Y direction, this one only has a X component. And in fact, I'm going to treat to the right as positive, so I might as well go ahead and put a little legend over here to say what my coordinate system looks like. So I'm going to say X points to the right and Y points up. And what I mean by that is the positive X direction is anything pointing to the right, and the positive Y direction is anything pointing up. So we now have that force. Now I'm going to go ahead and calculate the force FQ2. So in this case, I'm going to say FQ2 is equal to 8.988 times 10 to the 9th Newton meters squared per Coulomb squared, times, in this case, I'm going to put in the 2.78 times 10 to the negative 7 coulombs, times the 1.01 times 10 to the negative 3rd coulombs. And I'm going to divide all this by the distance between them. And of course, we see the location of Q is right here, and the location of Q2 is right here. And you might not realize it, but the fact that this horizontal part of the triangle is 30 centimeters wide, you could notice, for instance, that that's 3 times 10 centimeters. So for instance, let's look at this and realize that this is 3 times 10.0 centimeters. And if you find the other one is 4 times that exact same number, 10 centimeters, then you know it's definitely a 3, 4, 5 triangle. And in fact, this is 4 times 10.0 centimeters. So since I've got the 3 and the 4, that means this side over here must be the 5 times 10.0 centimeters. So we now know that distance is in fact the 3, 4, 5 triangle hypotenuse, which is 50 centimeters in this case. So I'm going to say divided by 50.0 times 10 to the negative 2 meters, and that's going to be squared. And when you put in this number, we actually get for this one, FQ2 is in fact 10.0946 newtons. And we can see again, we had 3 sig figs, so the 9, the 4, and the 6 are not sig figs. Now, it does help for us to notice the direction of this particular force. So it has to be along this line that connects the two, and I've already got a purple line showing that hypotenuse. And this one happens to be quite small, so I could choose to put the force right here. And that would be FQ2. So, and that's not a bad representation of it on a scale system, because one's 100 and the other one's 10. So that little blue is actually still a little too big, to be honest with you. But the big thing to know this about the diagram here is, because it's a 3, 4, 5 triangle, we know this angle right here is 53.13 degrees, because the big angle is always opposite the big side, which is the 40. That also means, of course, this one would be 36.87 degrees. So that's fair game too. If we were to look at this, we can see, for instance, that this FQ2 is going to have a x component that points to the left, which is a negative direction, and it's got a y component that points down, which is the negative direction as well. So we've got 2 components for FQ2, and both of them are negative, and this angle 53.13 is the same as this one. So let me go ahead and label this. This is FQ2 x component is that guy, and FQ2 y component is this guy. Okay. So all I have to do is to add these 2 vectors. I now have their magnitudes, but I have to find their components, the x components, the y components, and the z components if we had them. We can see from the diagram that FQ2 has an x and y component, but FQ1 has only an x component. So you guys might use TOA, or you might use some old horse came a hopping through our alley. Doesn't matter too terribly much. But the main thing is, you see for this angle right here, the opposite side is this one, and the adjacent side is this one. Okay. So now that I have that, I can say that FQ2 sub x, we know it's negative, so I write a negative a priori. So you just put that in there. You're just forcing it. You're using the physics of the situation combined with your knowledge of how you set up the coordinate system to decide on the magnitude and direction of the components. And the component direction has to come from trigonometry, but the component direction has to come from your choice and you recognizing that the choice is consistent with the positive or negative direction. So in this case, the x component clearly points to the left, so I'll put a negative there. And what SOHCAHTOA tells us is that the sine of 53.13 degrees is equal to opposite, which in this case would be FD FQ2y, excuse me, not FQ2y, but F opposite of FB, yeah, FQ2y over the hypotenuse, which is FQ2. Similarly, this diagram tells us that the cosine of 53.13 degrees is equal to adjacent, which would be FQ2x over hypotenuse, which is FQ2. So you can see you have to multiply FQ2, the magnitude, times the trig function to get the actual magnitude, and that's what I'm going to do now. So I'm going to take the magnitude of Q2, of FQ2, which is 10.0946 newtons. And since I want the x component, we figured out that that must be the cosine. So I'm going to do cosine 53.13. Notice I'm using 4 sig figs on the angle, and I've got 3 sig figs for everything else. So that's good. You always want to have at least the same number of sig figs, but ideally even more. So now I take the cosine of 53.13 and multiply that by 10.0946 and a negative number. So I ultimately get for this guy is negative, this is the x component, right? Yes, and the x component should be the smaller one. Yes, which is negative 6.05. Whoa, I erased everything. 6.05 68 newtons. Again, I use 3 sig figs and 4 sig figs, so the answer's got to be the 3 sig figs. So those two are extras. And I'm just going to double check this with my calculator real quick. I calculated it earlier, but I just want to make sure. So 10.0946 times cosine 53.13 gives me 6.0567. Yes, that's good. Okay. Now I've also got to do the same thing for the y component for Q2. Again, this one's negative, so I'm forcing it by putting that negative right there. And again, from the sign that I have written up top, in order for me to get to FQ2y, I have to multiply FQ2 times the sign. So FQ2 is 10.0946 newtons times the sine of 53.13 degrees. And of course, that's going to give us a negative number. And this time it becomes 8.0757. So again, I put in only 3 sig fig numbers except for the angle, which was 4 sig figs. So I should have 3 sig figs. That means the 5 and the 7 are not sig figs. So I now have the x component of the FQ2 and the y component of the FQ2. I can easily write the x component of FQ1. That is obviously pointing in the positive direction, and it's the whole vector. So I'm going to put positive 100.764 newtons with these 3 digits not significant. And then I'll do FQ1y component. That one is actually 0. So now the way we add vectors according to that formula, FQ is equal to FQ1 plus FQ2. What that means is FQX is FQ1x plus FQ2x, and FQY is FQ1y plus FQ2y. Okay. So we now say that the FQ x component is, of course, 100. All right, hold on a second. 100.764 plus, now I'm going to say plus negative 6.0, so negative 6.0568 is the x component. So I'm taking 100.764 plus negative 6.0568, and that gives me I won't go ahead and write that, plus negative 6.0568 newtons. So notice this first number is only good to the first whole number, and the second number is only good to the second decimal place. So I've got to round my final answer to the whole number place, which in this case would be 94.707 newtons. But like I said, the only valuable number is up to the 4. So the 7, the 0, and the 7 are not sig figs. Now I've got to take and find FQY, and of course that's FQ1Y, which we know is 0. And we're going to add to it FQ2Y, which is negative 8.07. So this is going to be negative 8.0757 newtons. And that's our Y component of our total force. Now, to make sense of that, we're supposed to take and draw these back on a coordinate system. So what I'm going to do is use this lasso I have here and grab all this stuff and copy it to the next page. I'm going to say copy, and I already had that drawn here. I actually had that drawn several times. Let me see what I'll do. That's a bunch of stuff here. Okay, I'll just jump to here. Now I'm going to say paste. Okay, so I now have all that information that I need to be able to have from the previous page. So now all I have to do is remember that I already said our coordinate system was based on y pointing upward and x pointing rightward, like that. And what we just found was that the x component of the force is quite big. I'm going to represent it with this nice Carolina blue vector. Okay, it's not exactly Carolina blue, but it's a pretty color blue, and I like it, and everything about Carolina is awesome, so I'm going to say that's the case. And you can see that that vector has a magnitude of 94.707 newtons, and it points to the right. And then I have another vector, which is really, really small compared to this one. I'm going to draw it a little bigger than it should be, just so we can see it at all. This should be 8.0757 newtons, like that. And that means the total vector force should be a arrow from here to here, and that's FQ. Now, this is also an angle that I'll call phi, and now I've got to go about finding the quantity, the component of, or excuse me, the magnitude of the total force and the direction of the total force. So first off, the magnitude of the total force, which is often written like that, but you can also write it as FQ vector and then put absolute value bars around it, because that's also means the magnitude. But according to the Pythagorean theorem, since this is a 90-degree angle, we could use the Pythagorean theorem. And what we're going to have is 94.707 newtons squared plus negative 8.0757. And I just put that in just to remind you that it was negative, but let you see that even if it was, it wouldn't matter because you got to square it. What I will tell you is that when I square the 94.07, let's see, 94.707, that gives me 8,969. Uh, but I only have two sig figs, so that's to the nearest hundreds place. So I'm going to write this here just to keep track of sig figs, even though a lot of people don't care about it. I just want you to understand how they're getting the sig figs that they should be getting. This one's good to hundreds. Notice I said with an S, not with a TH. Now the other one, 8.0757 squared, that gives me 65.21. I only have, in this case, I only had two sig figs, so that only gives me to the nearest whole number. In other words, this is to the ones place. Okay, so when I go ahead and do these two, I'll take the square root of 94.707 squared plus 8.0757. That's also going to be squared. And that gives me the square root of some god-awful number. But the main thing is, when I go to add those two numbers, I know I'm only allowed to go to the hundreds place for the first one and to the tenths, I mean the ones place for the second one. So 9034 is what I get. So I'm just writing this out so you know. I get 9034.632 newtons squared. And I'm taking the square root of that. But the whole point is to show you that uh, I've got this guy has those three digits being non-significant. Uh, and also, since the 8, when I squared that, that only gave me to the nearest tens place. So basically, I only have, actually, I said to the nearest hundreds, and I think I meant to the nearest tens. Let me double check that. 94.707 squared. Yes, so 94.707 is two sig figs. Yes, that is to the hundreds place. So really, I'm not supposed to have this digit or this digit, so I only get out two sig figs. So my answer is going to be 95.05 newtons for the magnitude of the force, but again, the 0.0 and the 5 are not sig figs. So I've got the magnitude. Now the phi is the inverse tangent. Remember, some old horse came a hopping through our alleys, our TOA, which means tangent equals opposite over adjacent. The opposite, of course, is 8.0757 over adjacent, which is 94.707. So we got two sig figs divided by two sig figs. So I'm only going to get two sig figs, but I'm going to say tangent inverse parentheses 8.0757 divided by 94.707, close parentheses. And that gives me 4.874 degrees. But again, I only had two sig figs in each of those, so I'm only allowed to call that 4.8 degrees. So I can finally say the total answer is F total, which is also equal to FQ, is equal to 95.1 Newton. Notice I underlined the 1. I gave everybody an extra digit, but I let them know it was an extra digit and shouldn't be part of the answer by underlining it. And it's actually notice that's measured clockwise downward from the positive x-axis. So clockwise means negative 4.87 degrees. Again, I gave one extra digit for sig figs. So that's the answer. Hopefully that'll help you work out the difficulties you might have with vectors and components and all that good stuff. But that's enough, I think. Feel free to send me any emails or anything like that you might have. But keep working, and thank you for your time. Have a good day.